Welcome back. Useful probability distribution. In this session, we're going to discuss a number of important distributions which have been found useful for describing random variables in many applications. One of them is the geometric distribution. A geometric random variable x with parameter p has the probability distribution p x equals to n, which is equals to 1 minus p, and p raised to the power n, p being the probability of the geometric random variable x. For this distribution, we have the generative function equals to 1 minus p over 1 minus pz. The expected value of x, or the expected value of the geometric random variable x, is equals to p all over 1 minus p. And then the variance, the standard deviation, sigma squared of the geometric random variable is equal to p over 1 minus p all squared. And then the coefficients c squared over x is equal to 1 over p. So the coefficients of the geometric random variable is equal to 1 over p. The next distribution we will need to consider is the Poisson distribution. The Poisson random variable x with parameter mu, that is the mean mu, has the probability distribution equals to mu raised to the power n all over n factorial times exponential minus mu, n starting from 0, 1, 2, and so on and so forth, being discrete. For the Poisson distribution, it holds that the probability generating function is equals to e raised to the power minus mu into 1 minus z. The expected value of x for Poisson distribution is sigma squared x, which is equals to the mean, and the coefficient of variation is 1 over mu. The third distribution is the exponential distribution. The exponential distribution assumes that the density of an exponential distribution with parameter mu is given by f of t is equals to mu e raised to the power minus mu t greater than 0 times t greater than 0. The distribution function equals 1 minus e raised to the power minus mu t greater than or equals to 0. For this distribution, we have the Stiegis function, the Laplace Stiegis function transform, to be equals to mu over mu plus x. The expected value of x is 1 over mu. The standard deviation, sigma squared, is equal to 1 over mu squared, and the coefficient of variation is 1. That's for the exponential distribution. And an important properties of exponential distribution variable x with parameter mu is the memoryless properties. This property states that for all x greater than or equals to 0 and t greater than or equals to 0, the probability of x equals to x plus t, such that x is greater than t, is equals to probability of x greater than x, which is equals to x raised to power, which is equals to e raised to power minus mu x. So, for the remaining lifetime of x, given that x is still alive at time t, is again exponentially distributed with the same mean 1 over mu. So, we often use the memoryless properties in the form of probability distribution p, probability of x less than t plus delta change in t, delta t, such that x is greater than t, is equals to 1 minus e raised to the power minus mu delta t, which is equals to mu delta t plus other functions of delta t as delta t tends to 0. Then we also need to look at other distribution, which is the Erlang distribution. A random variable x has an Erlang k distribution with mean k over mu if x is the sum of k independent random variable x1, x2 up to sk, given that or having a common exponential distribution with mean 1 over mu. The Erlang distribution is actually a sum of the exponential Poisson exponential distributions, rather. The distribution of an Erlang distribution k with parameter mu is given as mu into mu t raised to the power k minus 1 over k minus 1 factorial times e raised to the power minus mu t. The distribution function is also equals to 1 minus summation of mu t raised to the power j over j factorial e raised to the power minus mu t. This parameter mu is called the scale parameter. K is the shape of the parameter, and a phase diagram of the EK distribution is as shown in figure 2.1. Phase, K mu will continue to until k tends to 0. So, the mean, the variance, and the square coefficient of the variance are equally presented as expected value of x is equal to k over mu. The variance s squared is equal to k over mu squared, and the coefficient of variation is 1 over k. So the Laplace transform is given by mu over mu plus s raised to the power k. Then we also need to look at other, let's leave this one and check some other properties. We look at the Poisson process. What is Poisson process? That's the beginning of the application of the distributions. Let nt be a number of arrival in 0 to time t for the Poisson process with rate lambda. The time between successive arrival is exponential distribution with parameter lambda and independently of the past. Then nt has a Poisson distribution with parameter lambda t given at time t. So the Poisson process at n t equals to k is equals to lambda t raised to the power k over k factorial e raised to the power lambda t, and k lambda k lambda t, yeah, k starting from 0, 1, 2, and so on and so forth. So the mean, the variance, and the coefficient of variation of nt is equals to the mean expected over nt is equals to lambda t, the variance sigma squared nt is equals to lambda t, and the coefficient of variation is 1 over lambda t. Please take note. From 2.1, it is easily verified that probability of arrival at time t to t plus change in t, small change in t, is equals to lambda t is equals to lambda delta t plus O delta t. Now, when t is so small, then probability of arrival at t plus lambda t is approximately lambda times change in the small t, small change in time. The diagram here shows the arrival rates in Poisson distribution and Erlang distribution. The arrival occurs at random. In Poisson, at random. At time t, there may be 0 arrival. At time t, there may be 2 or more arrivals. But for Erlang, it seems to be uniformly distributed. The rates at which arrival occurs varies sparingly. We also need to look at 2 important properties of Poisson process. The first one is called the margin. The second one is called the splitting. For the margin, suppose that nt and n1 of t and n2 of t are 2 independent Poisson processes with respective rate of lambda 1 and lambda 2. Then the sum of the 2 independent Poisson process n1 and n2 of 2 processes, again a Poisson process. with the rate of lambda 1 plus lambda 2. For splitting, suppose the independent Poisson process NT is a Poisson process with rate lambda, and each arrival marked with probability P independent of all other arrivals. Let N1 and N2 denote respectively the number of marked and unmarked arrival in time 0 to t. Then N1 of t and N2 of t are both Poisson process with respective rate lambda p and lambda 1 minus p, since they are independent. And these two processes are independent. So the Poisson process remains Poisson process under splitting and matching. Exercises. Thank you very much.